Hi, everyone. I've had a few questions about a problem on the homework. So the problem asks you to consider the series whose terms look like this. So you can see that each term in the numerator is a product of odd numbers, and the denominator is a product of even numbers. And in each term, right, we're adding an additional number in the numerator and denominator. So our general term looks something like this. And the problem asks you to apply the ratio test, apply the root test, and then apply a new type of convergence test that we haven't talked about before. And what I've had several questions about is I've had several students reach out who are having difficulties applying the root test here. And it is a rather tricky calculation. So let's take a look. The root test asks us to find this value rho, which is defined to be the limit as n goes to infinity of the nth root of the nth term of the series. So looking here, right here is our generic nth term of the series. So here we are really trying to calculate rho is equal to the limit as n goes to infinity of this product. And we're taking the nth root of this. I'm going to rewrite that as to the 1 over n. Now, here we can take advantage, in order to calculate this, we can take advantage of a trick called logarithmic differentiation. The idea being, if I take the natural logarithm of both sides, so I'll get the natural log of rho is equal to, so I have the natural log of this whole thing, but since natural log is a continuous function, I can actually pull this limit out. And I will get that this is equal to the limit as n goes to infinity of the natural log of this term. So natural log of this to the 1 over n. Now, the advantage of this is this allows me to apply properties of natural logs, namely that I can actually have natural log of a to the b, that's equivalent to b times the natural log of a. So this exponent here can in fact come down out front. And so this is equal to the limit as n goes to infinity of 1 over n times the natural log of this term. Now, the question then becomes, okay, I know what happens to 1 over n as n goes to infinity. That's going to go to 0. What happens here to this term? Well, I don't want to give away the whole problem. So what you want to do from here is look at this, but almost think about this in descending terms. So if I were to just think about this as like 2n minus 1 times 2n minus 3, and then to keep doing this until I get times 5 times 3 times 1, I might sort of notice that this is going to be some sort of polynomial in n, right? Similarly, if I look in the denominator, I have 2n minus 2, right? So on and so on, all the way until I get down to 6 times 4 times 2. And again, this looks like a polynomial in n. And these polynomials will have the same leading coefficient, okay? Well, let me be careful. You have the same powers of n here. You'll want to look at coefficients, but notice that this term is going to 0. So if you can prove that this goes to any bounded number, then the whole limit will go to 0, right? So when I look at this term inside, I might say, okay, how many terms do I have, right? So down here, I've got 2, 4, 6, I've got all the way up to n terms down here, right? And if I were to take these, I could factor a 2 out. I look at all of the coefficients here, right? Now I have to be a little careful about how I count these. I could find essentially on the top and bottom the ratio of the leading coefficients. This is then a polynomial in n. That will actually help me determine what this converges to in the limit. And then hopefully I'll be able to show this thing is maybe bounded. Okay. If I can do that, then that would give me, if this term is bounded, this term is going to 0, that limit will be 0. And then if that is the case, then I know that natural log of rho, that's what I want to find is rho. I then know natural log of rho is equal to 0, and I can use that to find rho. So hopefully this has provided you with a little bit of an idea for how you might calculate the limit needed in the ratio test for this problem.